What's going on, linear algebros? It's Mr. C here, and in this video I'm going to help us navigate our way through the rest of the notes for section 4.6. In particular, this video will show us how to complete the example that starts on the top of page 2 of the section 4.6 note packet. So we're going to start with part B. And in part B, we're to compute the transition matrix from the basis B to B prime. And so much of this work is going to mimic our work from part A. You'll see over to your left, I have a workspace heading for computing the components of the basis vector u sub 1 relative to the basis B prime. Much like with part A, we basically just want to rewrite the basis vector u1 as a linear combination of the basis vectors from B prime. And so you would start out with this equation. You want to say, okay, if I want 2, 2, like how much of the vector 1, 3 do I need, and how much of the vector negative 1, negative 1 do I need? And that quickly bounces us into a matrix equation such as this, and solving for C1 and C2 tells us just exactly how much of U1 prime we need and how much of U2 prime we need. And it turns out that we don't need any of the vector 1, 3. We only need negative 2 times the vector negative 1, negative 1 to get 2, 2. Now hopefully that makes sense, because if you multiply this vector by negative 2, these turn into positive 2's, which that's exactly what we're looking at the components of the vector on the left. You'd follow a similar thing to figure out the components of u sub 2 relative to the basis vectors B prime. And so here's the equation that you would set up. Bounces us into a matrix equation setting, and solving for C1 and C2, we see that C1 is negative 5 halves and C2 is negative 13 halves. So this tells us that we would need negative 5 halves of the vector 1, 3 added to negative 13 halves of the vector negative 1, negative 1 in order for us to get the vector with components 4, negative 1. Now, each of these solutions for C1 and C2 are going to populate the columns of the transition matrix, which takes us from the basis B to the basis B prime. Now, you'll notice that I added an important note at the bottom of this solution. It turns out that if you find the inverse of one of these matrices, it gives you the other transition matrix. So in particular, if we were to take the inverse of the matrix that we found in part A, transition matrix from B prime to B, if we were to take the inverse of that, we would get the same answer as what we're seeing up here. So kind of a neat little fact that can be handy from time to time. Alright, I'd like to help us work our way through part C now. A couple of things on the docket. Number one, we want to compute the coordinate vector W relative to the basis B. And the components of this vector W are provided for us. 3 is its first, and negative 5 is its second. Then we want to compute the coordinate vector W with respect to B prime. So one important thing to note right off the bat is that these components aren't with respect to the basis B just yet. When we're provided a vector such as this, we actually want to assume that this is relative to the basis I and j, so the standard unit basis vectors from R2. So this tells us that in order to get the vector W, we need 3 i's and negative 5 j's. Well, what would these components look like if we were to base it on the basis vectors from B? Okay, so that's the first thing on the docket, and I have the solution here. We're basically going to figure out what the components of the vector W would be with respect to the basis vectors from B. So you set up this equation again, where we kind of ask ourselves, how much of 2, 2 do we need, and how much of 4, negative 1 do we need in order to get the components 3, negative 5? Which of course takes us to a matrix equation, and solving for C1 and C2, it says that, okay, we need negative 17 tenths of the vector 2, 2 and positive 8 fifths of the vector 4, negative 1 in order to get 3, negative 5. So the coordinates, or I'm sorry, the components of the vector W with respect to the basis vectors B would be negative 17 tenths and 8 fifths. So with that in mind, let's work on the last part where we want to compute the components of the vector w with respect to the basis vectors b prime. Now, of course, you could simply rewrite the vector w as a linear combination using the basis vectors from b prime instead of the basis vectors from b. But I actually want to just show you how you can quickly use your transition matrix in order to do the same thing. So the components of w with respect to the basis vectors from b prime are going to be figured out by taking our transition matrix. We want the one that takes us from the basis b to the basis b prime, of course. We're going to take this matrix and multiply it to our answer from part 1. Now, your determination of the transition matrix to use is pretty easy to tell. You just want to make sure that the letter on the left of the arrow matches the letter of the vector notation that's to the right of the matrix. So as long as these two guys match, you're using the right transition matrix. All right, right underneath this, of course, is the written out version of each of these matrices. And when you multiply them out, you get -4, -7. So that's what the vector w would look like with respect to the basis vectors from b prime. And you're welcome to check that by writing the vector w first as some sort of unknown linear combination of the basis vectors u1 prime and u2 prime, and then solving directly. Alright guys, I'll see you in the next video. Thanks for watching.